A couple things before going back to watching water move around. I just sent an email, hope you got it, pointing out, saying that I'm going to cancel a class on Friday. I know you're all terribly aggrieved. It's right before the inauguration and stuff, and I figure the number of people who will come here will be small and conflicted. Other secret ulterior motives is, as of 6/19 yesterday evening, I now have a second grandchild. You know. So, a boy this time, a girl previous time. The pictures are cute of the girl kind of figuring out she's 3. It's like, huh, you know, little brother is now real. Am I still the princess? You all know those dynamics. We'll see how life, you know. Anyway, so I will secretly not be at the inauguration. Don't tell anyone. All right. I also pushed back problem set, the 6th problem set, just so I can cover more material. It's on the flow of air around a car, and so I need more time to get to that stuff. Any other thoughts about logistical stuff? One question that came in apropos of the problem set that you should just have completed, the problem set 5, you know, how can a plane turn in outer space? And a plane can't. So that is, you know, the question on the problem set asked about a spacecraft, which in movies are always drawn with all sorts of elaborate bells and whistles hanging off them so they look cool. In fact, in empty space, all that stuff that decorates the ship is irrelevant. There's nothing to push on. And to put this in proper order, aircraft push on the air. That's how they hold themselves aloft. That's how they steer. That's how they orient themselves. Everything there, it's all involving pushing on the air. And they do that with surfaces, and we'll learn how that all works next week, and give or take. Once you get outside the Earth's atmosphere, or any atmosphere, there's nothing to push on out there anymore. So having all these fancy surfaces like wings and tails and stuff, completely irrelevant. And that is why some of the spacecraft that are orbiting the Earth right now, or even going off into deep space, have all kinds of odd shapes, can orient themselves in any old direction. None of it matters. You can have a school bus orbiting the Earth, and whether it's oriented nose first, you know, front first, front back, who cares? It's just an object coasting through space, or following a path that's bent by gravity, but otherwise nothing else. So when you watch your next science fiction movie and you watch the people jockeying around in these fancy, elaborate-looking spacecraft, you know, a flying box is perfect. You know, a box is a perfectly good shape for a spacecraft. You don't need any fancy shapes. Is that addressing the question? Yeah. Okay. The other thing to point out is that because the only thing that a spacecraft in deep space has to work with, to push on it, is its own fuel. When it runs out of fuel, it is truly dead in the water. It cannot do anything except follow the path that inertia and gravity have intended for it. With nothing else to push on, I mean, short of like taking stuff, you know, pulling off the seat cushions and throwing them out the window, they have nothing to push on them at all. So you can't steer at all. All right? Having gone over that, what I want to do is I want to try to go through the water distribution in a somewhat different order. And Monday was, in my view, something of a train wreck. Let me try to do it in an order that I hope you can follow. And part of the problem, as I was thinking about it afterwards, is that it's easy to look back knowing everything and see how all the parts work. It's very hard to lay them out so that they're understandable at the time without the future already covered, without everything already covered. So let me try a different order, and that is to look at the flow of fluids in what's called steady state flow. And to set the stage for that is fluids are complicated. The way in which fluids flow is so complicated that it remains one of in effect, the great unsolved mathematical physics issues. There's an equation that describes how fluids should flow. It's called the Navier-Stokes equation, and it's one of the, I think that solving the Navier-Stokes equation in all its glorious detail is one of the Clay Mathematics Prize contestants. It's one I think you can get $1 million for solving this unsolvable differential equation, it's called. The point being that understanding how fluids flow is tough, and I end up getting caught up in them. Therefore, physicists and engineers and people trying to deal with fluid flow often make simplifications, or they pick a model that's close to the real story, but that is simplified in ways that make it doable, as opposed to just some horrendous thing that you can solve sometimes with computers just crunching away on numbers. But an example of why this stuff is so hard is, you know how well the weather is predicted, right? Predicting the weather a month from now, how reliable do you think that is? Well, right? You might as well just do astrology. So it's because the flow of the fluids in this, primarily air, but also water, are just so hard to do the calculations right. So we make a simplification often, and one of the wonderful, sort of the best simplifications for fluid flow is what's called steady state flow. And steady state flow makes the following assumptions to watch the flow of fluids. It assumes that the fluids are flowing steadily through a stationary environment. Nothing in the solid world in which the fluid is flowing is allowed to move. So, and why not? Because if a surface can move through a fluid, it can do work on the fluid, or negative work on the fluid. It can add or subtract energy. So don't let it move. Don't let it do work on the fluid. What the fluid's got in the way of energy, that's all it's got. An example of steady state flow would be a slow-moving river flowing between stationary banks. The banks are not adding or subtracting energy from the fluid. Water in a pipe. A smooth waterfall going down into something that catches it smoothly. A fountain going up steadily and not breaking into little pieces, but rather nice spray, smooth spray coming up and going down. The environment is stationary, and the flow has to be stationary. Not stationary, but constant, so that in effect you can't see any change from second to second in the flow. And my not jargon, but my off-the-cuff remark for like, how would you tell it's steady state flow when you can't distinguish a photograph of the flow from a movie of the flow? It just looks the same every second, so you can't see anything happening. You can make the flow visible momentarily, for example, by adding dye to the flow, so that you take water, which is clear, and you put in drops of dye, and you watch the drops of dye move through. That's how one would watch steady state flow flowing. And people actually do this. I mean, they actually do put colors into the flow and watch the things happen. Okay. In the world of steady state flow, there's a great simplification that shows up, and that is that if you watch the fluid that flows along, that starts at a specific point and enters the flow, and I hope you can visualize with me the flow of fluid through, I don't know, pipes or a bunch of pipes, a tub, all sorts of structures over here, and then leaves the view over on that side. All the structure is motionless. Okay? So if we watch the flow going through all this plumbing and stuff and come out the other side, and we start adding drops at one point in space at the upstream end of the system, those drops will follow the same path every time. Because we start at the same place, they follow the same path through the system and they leave view. The path that they map out, these drops put right there at the start, they map out what's called a streamline. And these words ended up in common language. You've heard of things being streamlined, and that used to be a name that people would put on products, a streamline such and such. what they're meaning when they're saying it is that this is a system that has streamlines, that allows the flow to be structured in this beautiful manner, as opposed to white water, which we'll come to later. White water is turbulent flow, where the flow is swirling around, and it's important in nature, but not for today. It's not part of steady state flow. If in white water you put the drops in, you watch them going in, and mapping out those streamlines, and then they get ripped apart into white water, and they're just a hash, nothing good anymore. So if you've got the streamlines, you have the smooth flow. It's called laminar flow. Again, we'll get to that kind of stuff. So the fact that steady state flow has streamlines, and they're not all identical. You can have streamlines that are different. Of course, they're different in space. The drops put here follow that path, and that streamline. The drops that are put down here, they follow a different streamline. They have different stories, and it's important to distinguish them. Don't compare them with one another. Don't assume they're identical. Okay, so where does this all go? It goes to an important observation made by Daniel Bernoulli and Leonard Euler. I should know when they lived, but it's about 200 or 300 years ago. That if you follow the water that passes along one of these streamlines in steady state flow, the energy per drop, which is my shorthand for saying energy per volume of the water, is constant along the streamline. And that seems like just, okay, an out of the blue statement that what are the consequences of it? Well, the consequences are substantial. Can I justify it a little bit? As a drop follows its streamline in this beautiful steady state flow situation, it can transform its energy between three different possibilities. Gravitational potential energy by going upward or downward in altitude. Kinetic energy by going faster or slower. And lastly, what's called pressure potential energy, which technically isn't a conventional potential energy. Potential energy is energy stored in the forces between or among things. This energy is present, but it's not literally in the drop of water. It's promised by somebody who is willing to replace that drop if you pull up drop out of the system. It secretly comes from the water company or a water tower or something. If that doesn't make any sense, don't worry about it. Pressure potential energy is every bit as good as an ordinary potential energy in the world of steady state flow. So it's in there. Three types of energy. These are three types of ordered energy, I should say. Why the word ordered? As opposed to thermal energy. Thermal energy is not counted in this story. So energy that's all disordered, it's ground up into dust. We don't count it. Furthermore, we're assuming that none of the ordered energy is turned into thermal energy. That is another assumption, it's another simplification. And it's not, in the real world, alas, water flowing or anything flowing through plumbing does waste some of its ordered energy as thermal energy by way of friction-like effects. So what are those friction-like effects? Well, they actually have to do with the syrupiness of fluids, what's known as viscosity. Honey, molasses, motor oil, they're syrupy, right? And if you try to move your hand around in a pot of honey, it's going to get tiring because you're going to be doing a lot of work on the honey. And that work's going to end up as thermal energy in the honey. So real fluids have viscosity, and viscosity leads to wasted energy. And so in this world of steady state flow I'm talking about, we're going to assume no wasted energy. No viscosity. We're just going to ignore it. So we've ignored viscosity, we've forbidden anything structural to move, and we've not allowed the fluid to start or stop its motion. We want steady. And in that world of steady flow, the only energies that we care about are kinetic, pressure, and gravitational, and a drop moving along one of these streamlines can exchange one of those for the other, but the sum is constant. The energy per drop all the way along the same value. And where does this come from? It comes from the fact that in the steady state flow, the water can't transfer energy from one drop to a different drop. This drop of water can't do work on that drop of water and pass along some of its ordered energy. because the boundaries are not moving with time. Everything's sort of sitting constant. The detail of why that works out doesn't matter. This is why it was done by great mathematicians, why they figured it out. It's complicated. But the fact that the energy is constant has much simpler consequences. I've set the stage with complicated story for simple observations. And that is that if you follow the flow along one of these streamlines in the world of steady state flow, and in many situations can be approximated as steady state flow, you can watch the energy go back and forth, okay, from one form to the other. And I was waving my hands wildly doing this last time, but now let me do it right and carefully. I'll set this aside for the minute. Lots of possible demos. Okay. So with this tank of water, this is where I was getting the story started. Let me tip this a little bit. So this consists of, yeah. I'll put the water in the tank, and right now the water is approximately at equilibrium. Everything's sort of settled down, and not unrelated but separate observation is that water then, when it is in equilibrium, it all seeks its level. That was a statement I said last time, which is just jargon for the top surface of the water everywhere in the connected plumbing is at the same level. If one surface was higher than the other, there's extra gravitational potential energy to be had, and the high level water will flow down to fill in the low level water, releasing potential energy, and everybody will be happy and in stable equilibrium when they're all level. So that's the case here. The water level here is there, the water level here is there, they're at the same level. If I lift this guy up, and I'm blocking the flow right now with my finger, but as soon as I let go, how wet are we going to get? Not too bad. Okay, now, for 1 second, not really steady state flow, big mass. Now we're effectively in steady state flow. Yeah, this is jiggling around. Don't worry about it. It's details, not totally irrelevant. But if I keep adding water here, so I did work lifting it up. I keep replacing this. Now I'm making it steadier state flow now by sort of keeping it all clean and neat. The water is starting with gravitational potential energy per drop. It's losing that gravitational potential energy per drop as it descends. Where's the energy going? It's going into pressure potential energy. And then it goes to the bottom, and then it starts ascending, going up. Where's the gravitational potential energy coming from? Out of pressure potential energy. And then it goes into the nozzle, and it converts pressure potential energy into kinetic energy. It flies up, converts kinetic energy into gravitational, and then turns gravitational back into kinetic. So it runs out fast, but you okay with the conversions, the fact that conversions are occurring? Questions about that? Why? Yeah, Rebecca. Can pressure potential energy only occur when it's in a tube? It can only go above or below atmospheric pressure when it's protected from the surrounding ambient air. So the pressure potential energy is out here in the open air is atmospheric pressure, which we'll see is actually there's still some energy in it. You can get that. But otherwise, it's a fixed value. And we have to protect it to shift it away above or below. So that's why the pressure potential energy becomes interesting inside the pipes or inside the nozzle, where it's protected. Is that okay? Thanks for asking the question. It's a good question. Okay, so we are indeed working in a ambient background of atmospheric pressure. And that sets a lower limit for pressure. We can go lower if we move the air out of the way, and we will shortly. Let me not do it right yet. So there are three kinds of energy, ordered energy available. Again, thermal is just we're leaving it out of the story. And I'll say also that we're working with water and not air. Is there a difference? Yes and no. For the most part, air does a great job of doing the same story. You can follow streamlines, and you can watch the energy go back and forth between gravitational, kinetic, and pressure. Air has one other possibility, though. It has one additional kind of energy, and that's the energy that is stored in the air by doing work on it, packing it tighter, smushing it. It's compressible. So air, because it's compressible, is more complicated than water because water is not compressible. The fact that you can squeeze air tighter and change its density, that adds another complexity to the story. So we'll stick with water for this story, and then we'll cavalierly use Bernoulli's equation to describe how airplanes fly anyway. Yeah, airplanes, the air is compressible, and it's not quite like flying in water. It's like you're flying in a gas, okay, but we can mostly ignore that difference, and will. So water zipping through the plumbing is trading its energy back and forth between these. Well, how do you force it to trade from one to the other? Is it just like rolling dice and deciding? No, it's doing it for specific reasons. Is steady state flow theoretical, or would it ever happen naturally? You can get very close to steady state flow, and in the laboratory people try to get as clean as possible to it. One thing you can't do is get completely rid of viscosity with only one or two very extreme exceptions. There are in nature some weird, there's superfluid helium, which actually has, in principle, zero viscosity. But that's, that's an exotic quantum effect. In general, viscosity is around. So apart from the fact that viscosity is a nuisance, you can get steady state flow. You just turn the flow on, and plumbing that's truly not moving, and you have the flow going for long enough that you can no longer see any evidence of the start. It's steady state flow. It's good. It will exhibit the behaviors that we're describing here. And if you use a very low viscosity fluid, you can get pretty close to perfect flow. All right? So to force the flow to switch its energy from one form to the other. And let me start with a nozzle. You've seen nozzles your whole life, too. You send a fluid through a narrow gap. I mean, I won't do it like that. I was going to put my thumb over a hose, but that brings up other issues that it brings up viscosity issues I don't want to bring up right now. But you know that if you send water that's coming through a garden hose and you neck down the garden hose with a physical nozzle or something, suddenly the water is traveling very fast through open air. What happened? The fact that you neck down the flow, that you start with a flow through a pipe this big, say, and then you shrink it down and make it go through an opening, an exit orifice this big, it has to speed up. Why does it speed up? Because water is incompressible, that was the rule, and if you're trying to bring in 1 liter, if you take suppose the water going through the big pipe, here's me trying to visualize the big pipe. And the water, every second it moves from here to there. That's a big blob of water that's just come through in that 1 second. And it goes by, and another blob comes through, goes by, and so on. If you want to get this much water to go through the narrow little neck that is the nozzle, it's going to have to go much faster because you're going to take this blob and you're going to have to squish it down. And I've always wanted to animate this, but I've never gotten around to it. This is hard. It's beyond my skill set. If you want to squish it down into a narrow thread to shove it through that little opening, it's going to become very long. So you're going to be moving this long slug of water through. It's going to have to go fast. My other analogy for this is on the highway. You got a 12-lane bumper-to-bumper traffic heading to the beltway around Washington, right? Life as usual. So it's totally bumper-to-bumper, 12 lanes wide, and you come to the construction site where it's suddenly 1 lane high. That construction site is literally the bottleneck, and everybody's got to go very fast through that in order for any speed to show up in the 12 lanes upstream, because all the cars are having to neck down and pass through that narrowing. So they have to go much faster in the narrow spot than in the wide spot. Any problems with that idea? So the flow has to speed up. That means it has to come up with kinetic energy. The flow before the nozzle was wide and slow. In and beyond the nozzle, it's fast and narrow. Where did the energy come from? It came out of pressure potential energy. If you look at the pressure before the nozzle, upstream of it, and after the nozzle, downstream of it, the pressure will have dropped. So that's what nozzles do. They give up pressure potential energy by letting the pressure drop, And that drop in pressure actually is responsible for accelerating the fluid forward. It pushes forward on the fluid. Remember, fluids accelerate towards lower pressure. It accelerates toward lower pressure, speeds up, and it leaves the nozzle traveling faster at lower pressure. And if it's exposed to the air, if it's out in the open air, we know what that pressure is. It's atmospheric pressure. So the water, let me get the nozzle going again, at least for a second. Sorry. There you go. There it goes. It's going. So the pressure before the nozzle is above atmospheric pressure, significantly perhaps, and after the nozzle it's down to atmospheric pressure. And in that transition from high pressure to low pressure, the water converts energy from pressure potential energy to kinetic. That's what gets it going fast. All right, so nozzles, narrowing, necking downs, cause the water to convert pressure potential energy to kinetic energy. The reverse, there are devices called diffusers, and you encounter these, the most common way I know that you encounter a diffuser, which is an anti-nozzle. The opposite of nozzle is the add-on thing you can stick on a hairdryer. Normally a hairdryer does two things at once. It makes hot air, and it delivers a lot of hot air, but it delivers fast-moving hot air, which is not necessarily what you want. Because yeah, your hair dries out, but it dries out in this style where it's off like that. So how do you slow down the air? You can slow it down by sending it through a sock or something. That's a waste of energy. So you force it to waste its energy. But instead, send it through a diffuser, which is a widening. And when you do that, the air slows down and it converts kinetic energy to pressure potential energy. And that's the effect of the diffuser. The air comes out slower. It happens to come out because of how the device is created. It comes out at atmospheric pressure, and you might think, well, it didn't raise its energy. It slowed down, but why? Where in the world? It doesn't have any energy. It came out at atmospheric pressure. The secret is that inside the nozzle of the air dryer, before the diffuser, the pressure is actually below atmospheric pressure. I said that there are ways in which you can go below atmospheric pressure and release even more pressure potential energy. If you drill a hole in the side of that hair dryer while the diffuser's on, the pressure hiding out inside there, it's a slight suction. It's below atmospheric. Another way diffusers form without even building one is just spray water against a wall. If I just sprayed a jet of water against the wall and let it get all steady, nice steady state flow, the water hitting the wall would spread out and slow down. You've done this. You just shoot a jet of water. It spreads out. It builds its own diffuser with no physical structure on the outside. And in the center of that place where it hit, where it's spreading out, in the center, which is protected by the surrounding water actually, the pressure is higher than atmospheric. And you know this because if that's your hand back there, you feel pushed on. You know when a stream of water or something hits your hand, you feel, whoa, it pushes you back. That's the rise in pressure that comes with the water bending outward, spreading outward, and converting kinetic energy to pressure potential energy. All right? Hopefully that's a familiar phenomenon. This is how you can blow stuff. You use it to clean stuff off the deck, right? You blow away all the leaves. It's that pressure rise that comes with slowing the water down and having its pressure go up instead. Okay, so I've used nozzles and anti-nozzles to convert pressure potential energy to kinetic or kinetic to pressure. How about getting gravitational involved? If you take a pipe to protect the water from outside air so its pressure can vary above or below atmospheric, send water up in a uniform pipe. So if you push the water up in a uniform pipe, it's gaining gravitational potential energy as it rises. Where did the energy come from? It comes from pressure potential energy. So the pressure at the bottom was high, and it effectively lifted the water to great height but low pressure. So it converts, so the pressure drops as the water rises. The fact that the pipe is uniform is very important for this part of the story because in a uniform pipe, water can't speed up or slow down. In other words, it can't change its kinetic energy. Whatever speed water enters a uniform pipe, it has to leave the uniform pipe. Otherwise, if it leaves more slowly than it arrives, it's going to accumulate. or if it leaves more rapidly than it arrives, it's going to run out. The pipe is going to go dry. So uniform pipes force the speed to be constant. Just like bumper-to-bumper traffic in a uniform road, the whole way everybody's going the same speed. Okay? So in a rising pipe, the water converts its pressure potential energy at the bottom to kinetic at the top. Gravitational at the top. Again, think first, dum-dum. If it does the reverse, if it descends, water descending through a uniform pipe converts gravitational potential energy into kinetic. Again, gravitational into pressure. Okay? And actually, if you have a big blob of water up here and let it descend like this out of a water tower, it converts gravitational potential energy into pressure potential energy. Now you've got a dandy source of high pressure water. This is most towns. They'll have a storage container that's up high, packed full of energy per drop by virtue of its being gravitational potential energy. They'll fill it at night and it's available for the whole day. So uniform pipes force the conversion of energy between, think first, pressure potential energy and gravitational pressure potential. Is that okay? Question about the nozzles, going back to nozzles. Is the water inertial after it leaves the nozzle? If it's shooting horizontal, yes. So once the water, I won't do it because it'll shut the door. If I tip the nozzle horizontally, so the water goes from high pressure through the nozzle to kinetic, it will coast inertially. Yeah, gravity's around it, eventually begin to descend. But if I tip it upward, now it's not inertial anymore because once it leaves, it will have kinetic energy and upward momentum, but it will gradually lose that upward momentum and kinetic energy as it rises. And it'll eventually become motionless for a moment, and then it will descend and convert its gravitational back to kinetic. All right? So you get inertial only, a nozzle, if you go into deep empty space and you have a nozzle, you shoot water out of it and it comes out, it'll be truly inertial once it leaves. And it will be at the ambient pressure, which if you've got air there, great. It'll be at air pressure. If it's an empty space, it's going to go right down to 0. Okay? The third conversion pair that I should say, we've got, in the pipe, we went from pressure to gravitational and gravitational to pressure. If we leave the pipe, go outside the pipe and look at a fountain going up and down, now the pressure the water is not protected from atmospheric pressure, so its pressure will go to atmospheric. The water pressure in a fountain or a waterfall is atmospheric. If it weren't, there would be acceleration. It would not be steady state flow. The air would accelerate. The air and fluids would accelerate from high pressure to low pressure, and it would fix the problem. You would very quickly end up with everything at atmospheric pressure. So a fountain shooting up, there's no way it can change the pressure. It's atmospheric pressure the whole way up. But the water can convert its kinetic energy down low to gravitational up high. And on the way back down, it converts it from gravitational back to kinetic. And so that's the whole story of this water in the pipe. It goes from gravitational here to pressure in the protected regime that is the inside of the hose, all the way. There's a little bit of it goes into more pressure down here and then less pressure there as we're jockeying back and forth between gravitational and pressure in that U-shaped piece. In the nozzle, it's being forced to turn pressure into kinetic. This is atmospheric pressure here, so the pressure doesn't change anymore. It goes from kinetic to gravitational back to kinetic. Right? Oh, that was pitiful. Getting the steady state flow involves things like not having air bubbles in this sucker. Go, air bubble will go. Okay, well, it'll blow through. Okay? And among other things, you notice the water rises back to its start. That wasn't steady state flow, that pulse. That was the bubble coming through. And during this, when the bubble's going through, you can have weird moments in which This portion of water gives energy to this portion of water, and that portion of water ends up with more energy than it deserves. And it does briefly blasts up extra high. But in the steady state flow, we go from a certain energy always to the same energy. And that's why the water can never go higher than it started from. And sort of among the public service announcement parts of this, when you're fighting a fire, which you're supposed to in the last problem, the water has only so much energy per drop in a steady state flow situation. And if you don't give it enough energy to reach the fire on a 10th floor fire, it's not going to reach there. It doesn't matter whether you move the nozzle up or down. In fact, let me do that. More water. I've been moving up and down the source, but I haven't moved up and down the nozzle. Remember, if I pull this up, the water can rise no higher than its source. But if I lift the nozzle, it doesn't help. Right? The water still goes to the same height. It's still only got the same amount of energy per drop. Right? That's pretty convincing, actually. I've never done that before. But I like it. Ah, you're there at the invention of, great, okay. Any questions about that stuff? Just more firefighter stuff. I've had a lot of firefighters over the years come through class, and you learn things like if they're trying to fight a fire that's higher than their one pumper system can reach, basically the one pumper can't deliver enough energy per drop to reach the 15th floor. They'll daisy chain pumpers. They'll take the water out of the fire hydrant, which already comes packed with a certain amount of energy per drop. They'll go through the first pumper and get more energy per drop, and they'll go through the second pumper to get more energy per drop, more pressure potential energy initially, and then it goes up to kinetic and or gravitational. So they can reach higher fires. Okay? Because it's there. If I start with higher energy water, which is up there again, and I let it through, there it goes. It can go no higher than it started from. The fact that it doesn't quite go up to where it started from is an indication that we're wasting a little energy as thermal. But again, if I climbed up higher, the water still wouldn't squirt any higher. It's only got so much energy per drop. Okay? Now, having done this, I think I can do a somewhat better job, I hope, of showing you a siphon. In the siphon, if I have to get the flow started, and that's not steady state flow. Always love the taste of random water. Okay. Here, I've got steady state flow going again. The water is starting here at atmospheric pressure, motionless at a fair amount of height. So it's got some gravitational potential energy, but essentially no kinetic and no pressure potential energy. It's rising in this pipe. Where is it getting the energy? It's converting ambient pressure potential energy to gravitational. It's going below atmospheric. In this protected environment at the top, its pressure doesn't have to be atmospheric or greater. It can be less than atmospheric. There's a partial vacuum up there. And the water then, it converts pressure potential energy to gravitational back to pressure potential energy and flows out the bottom. So this is another weird example of steady state flow in action. It'll always go from the high one to the low one. So if I reverse these guys, it'll go backwards. But the pressure at the top is below atmospheric. And the higher I bring that, the lower it goes in pressure. The lowest it can go is to 0, no pressure at all. And that will occur about 10 meters up there. And a siphon can't work any higher than that because there's no more pressure potential energy to be had, even if you have access to low pressures, even if you have access to vacuum. Okay. One other odds and ends. Once I break the flow, I ruin the steady state flow. Let air in, the whole thing stops behaving. This is just me trying to illustrate that the act of pumping and delivering pressurized water takes work. Therefore, the water is effectively carrying with it some energy. And it shows up in most plumbing as pressure potential energy. This is it's somewhat of it's not a true potential energy, but it's pretty close. This type of a pump, I can fill the syringe is going to be the pump. So it's a piston and cylinder. When I pull the piston out of the cylinder, I create an empty space with essentially nothing inside. Well, that's a vacuum, the pressure of which is 0. So atmospheric pressure then pushes the water out of the container up in to fill that void. There's a pressure imbalance. The pressure imbalance is one in which the container has no pressure in it. So the fluid accelerates and begins to flow towards the container. Okay, now it's in the container, and it flowed in through a one-way valve that won't allow it to go back. Instead, the water has to go out a second avenue over there, and there it comes out. So I can bring it in by creating low pressure inside the piston cylinder structure, and then I can get it to leave by creating high pressure in the piston cylinder structure. And in each case, I'm doing work. I'm exerting forces on the syringe piston, and it's moving in the direction of my force, so I'm doing work. The most important detail I want here is the act of pumping pressurized water and delivering it is a way of doing work on things. It involves mechanical work. It's actually a lot of mechanical work. The water company consumes a lot of energy delivering water to your house. If you don't believe this, try pumping water out of a creek to fill a swimming pool with a hand pump of some sort. You will be exhausted. You are doing the work you're doing, lifting the water, pressurizing it, delivering it through the hose, is enormous. I could pursue that, but I'm going to leave it. I want to do 2 more demonstrations before I run out of time. What I do want to say is that well pumps. Some of you have houses that have pumps, have wells, and getting the water out of the well is an issue that all involves all these energy. It's all this energy stuff. If the water table in your well is within reach, is only 5 feet down, I mean, there's the water. You can put a straw in it and suck the water up and get it to your mouth. You can use a suction pump, a pump that lives up on top and basically behaves like you sucking water up and then delivering it, right? So there are pumps that live on the surface and that draw water up by creating a lower pressure above the ground than atmospheric down there where the water is, and the water is then lifted by atmospheric pressure to the pump. Hopefully that's followable. If the water level is way down in the ground, 100 feet down, you can't do this any more than you can stick a straw in it and lift the water to your mouth, because you're not attracting the water, you're letting atmospheric pressure lift the water to you. And if full vacuum at the top and atmospheric pressure on the bottom are present, they can only lift a column of water that's about 40 feet tall, no more. The water gets too heavy at that point to be lifted by atmospheric pressure. In that case, you can't have a surface pump sucking water up. You have to immerse the pump at the bottom in the water and push the water up from below. So you will, if those of you who end up with pumps and wells in your future, you will discover that if it's a deep well, you're going to need a pump down there in the bottom pushing up. Okay? Let me do these demos before I lose them. Okay, here are the demonstrations. I told you that atmospheric pressure is sort of the background pressure that we live in, and you can't do much with it for the most part. You can go above atmospheric pressure and do interesting things, but going below atmospheric pressure is sort of exotic. It does show up in the siphon. It does show up in a few other gadgets around, but I'm going to go whole hog and get it involved here. I need somebody to help me with this one. Can I have a helper? Yeah, I'll go for Alex again. Okay, we're going to take the air out of this pipe. But before I do that, we'll put a ball at this end. Your job initially is going to be to hold the seal over here. Okay, so you're going to seal this side of the pipe. Okay, so you have to hold this in place until I turn a vacuum on and it gets grip. Okay, I'll let you do that. And I'm going to cap this end and take out all the air. So if we get a good seal, I think we got a good seal. I think you ought to be able to let go. Okay, you can come over this side. And there's going to be no air inside this. There's a ball hiding right in here. And when Alex, we're going to let the pressure go down pretty much right down to the bottom. He's going to knock this plug off. We've got seals at both ends that are removable. Alex is going to remove this seal. The air is going to rush in there because it's going to accelerate to lower pressure. This is atmosphere. It's not zero. That's zero. It's going to accelerate in here and convert this pressure potential energy into kinetic to go through there. The speed of its motion when it converts all this pressure potential energy into kinetic is about 200 miles an hour. And it's going to whisk the ball with it. And the ball is going to come out about somewhere 150, 200 miles an hour out that side. So don't blink. It comes out fast. Over the years, I've shot apples out of this, tennis balls, baseballs. The apples are a problem. They hit the wall and they turn into applesauce. And the splatter gets up to about the third row. Okay? So, maybe. There have been other dents. Most of the dents get patched up. But we've shot a lot of stuff out this end. Okay, so it's now under vacuum. So you hit that and break the seal, and the ball will come out really fast. You got to hit it hard. Thank you. We have shot, I first made this for a television show with James Brown, and we shot baseballs with it. They go about 400 or 500 feet. They come out at 150 miles an hour. The last thing to do here before I let it go, is this guy going to work for me? Just to show you that air, these fluids have a real life of their own, so to speak. And this is, can you see them? It's a vortex cannon. It's shooting smoke rings. And then, if we get it really good, you can get the smoke rings. They come out. It's all gas and gas. It's all the dynamics of fluids and fluids. Are they visible? Oh yeah, they're. Yeah, I want to make sure that get one or two at the camera if I can. And when they hit you, you can feel them. You getting it? Anyway. They're swirling. They're actually crawling forward. The outside, they're crawling this way. The middle goes forward, and the outside goes back, and they're crawling forward. Anyway, we'll play more with this on next Monday. So have a good rest of the week, and we'll see you on Monday.